여기들 아세요? 마이크를 소리를 조절하는 방법도 있어요? 스피커 말고?
네, 그 오디오, 맨 왼쪽 아래에 오디오 보이시나요? 그
예,
오디오 옆에
예,
예.
예,
그 쌀표 모양이 하나 있거든요.
예,
그걸 누르시면 오디오 설정이 있어요.
오디오
예.
설정.
네,
예.
그걸 하시면 이제 마이크랑 스피커 소리를 각각
아,
조절할 수 있습니다.
이건 스피커고. 마이크는
아,
볼륨이 100%로 돼 있는데, 내 거는.
스피커. 여기, 그러면 스피커를 내가 조절할 수 있구나, 여기에.
네네네,
거기도
맞습니다.
있고, 그 컴퓨터 자체에도 또
예, 컴퓨터
조절할 수
자체도
있고.
있고요.
예. 여기도 스피커. 이거는 이중으로 돼 있네. 예. 스피커.
어떤 조교님, 제 목소리는 이 정도면 적당하나요?
네, 잘 들립니다.
아, 그럼 됐습니다. 난 이거를 거의 안 써봐서, 이게 1년에 한두 번밖에 안 써봐서, 이게 항상 익지 않아가지고,
잘 들립니다. 감사합니다.
감사합니다.
내
조교님은 어느
마이크가,
기계과인가요?
아, 네, 기계과에 있습니다.
아, 감사합니다. 조교님 이름도 모르는데. 조교님 이름은 뭐예요?
아, 저 안찬희입니다.
네, 안찬희.
네.
감사합니다.
hey, today we have a special invited lecturer, Professor Jin Subak. He will uh, introduce about the Earth strength subject. And as I told you before that Professor Park has been working for Hyundai Heavy Industry for a long time. So he had a lot of experience in industry. So please welcome Professor Park. So I hand over the microphone to him.
들어갈까요, 교수님?
Yeah, yes, please.
공유, 소리 공유 체크하고, 공유를 다시 한번 눌렀습니다. 됐네요?
Yes,
Yes.
you can open your PowerPoint. Yes, I can see your slide set.
화면,
Yes, let's go ahead, please.
okay. Thank you, Professor Han. Good afternoon, everybody. My name is Jinsu Park. I'm very glad to give a lecture for my major structural analysis and design. Actually, I worked for the heavy industry, the number one shipbuilding company for more than 30 years before I came to KAIST, where I'm working on the cooperation between KAIST and Hyundai Heavy Industry Group.
요? 아니, 안 왔던 것 같은데.
I think most of you may be not familiar with this subject, so I'll try to explain conceptually. This is a scene of part of Hyundai Heavy Industry yard at Ulsan, Korea. In the evening, a very nice picture, isn't it? Do you see this red, very big structure? It's called a Goliath crane. So these cranes are the symbols of shipbuilding yard. In general, when we are talking about ship design, I think there are three key things that we are concerned about. The first one is performance and safety and efficiency and economics. The first one, performance, is about how fast a ship goes or how large amount of cargo it carries. The second on safety is the ship should be strong enough to endure the ship loading, the serious loadings during voyages. Third one is efficiency and economics. Is the problem of low fuel consumption and low maintenance cost. So today's lecture is related with the second topic, safety, structural ship strength. Before I get into the subject, hull strength, I'd like to show you an interesting video about strength test of small structure. Soda can, you may be very familiar with this small structure. However, have you ever thought about its strength? How much weight can this small soda can hold? It's interesting question. Generally, this can is made of a very thin aluminum, about 0.8 millimeters, in order to be made light. So in the left photo, you see in the opened and empty condition, it collapsed under the load of about 55 kilograms. How about the right one? In the unopened and liquid full condition, how much load will this structure resist? Can you guess? Let's see the test result.
Aluminum tank, like soda can or space rocket, it's going to be much stronger when there is some pressure inside. So I'm going to say that it's going to be at least twice as strong with the soda in it. So here we go.
Weight is going up. 100. 200.
Whoa. Oh.
300. Yeah.
Oh, it's going to
Ripple.
go!
Oh, yeah, it collapsed. Before it ruptures, deformation becomes very large. Oh, yeah.
That was really nice. And let's see the result. 360 kilograms, so way more. Yeah, that was really nice.
360.
And it failed like really slowly first before exploding.
Yeah, it went up to 360 kilograms. Is about 7 times bigger, higher than empty one. So from this test, we know that this kind of strength test and evaluation is needed to determine the structural design, for example, the thickness. So likewise, ship hull strength should be designed to resist a kind of maximum loading by proper design of structure. The main target of this lecture is large commercial ships. In case of commercial ship, our main concern in the initial design stage, how big load or what kind of loading can break the ship hull in real voice, in actual voice. In other words, what kind of wave and cargo loadings that should be considered in the initial design stage. So design purpose of hull strength is to ensure structural safety in the lifetime of, for example, 20 years or so. Here is a photo showing entire loss of hull strength. Maybe it underwent excessive wave loading around the center part. Actually, this kind of structural catastrophe happens, but even though it's very rare. In general, the type of ship is classified by the cargo it carries. The bulk carrier carries grain or coal. If the ship carries oil, we call it tanker. Of course, container ship carries containers. Car carriers carries car. So similarly, gas carrier and cruise and ferry. There are many types of ships according to cargo types. When we talk about ship, it may be defined in many ways. Particularly, when we limit our concern to general commercial ship, then the ship is defined to be a large watercraft which travels the oceans and sufficiently deep waterways. And also it carries goods and passengers supporting specialized missions. By the way, hull is meant to be the main structural part of ship, and the main loading against the hull is waves and cargoes. And the hull is optimized for low cost and sufficient strength in order to have a required performance and strength. Here is a photo showing hull structure. Most of the structure is called cargo hold and bulbous bow, engine room, etc. It would be interesting to think about how big is the largest container ship. The largest one, I mean the ship length of the biggest container ship is 400 meters. And it's about 60 meters wide. So the largest container ship looks like this. It carries 24,000 container boxes of this 20-foot containers. It carries a tremendously large number of containers. More than 50% of the container boxes are stacked over the upper deck, as you can see from this photo. It is interesting to compare ship lengths with famous buildings. It's a little bit bigger than Eiffel Tower in Paris, and a little bit smaller than Oriental Pearl Tower in Shanghai. So I mean, the size of ship is very, very big, bigger than we imagine. Actually, very so about four times bigger than Sackville. Here, I'd like to explain more about hull. Hull is said to be a watertight body of ships. It is a main structural part, including cargo holds along the whole ship length. Also, it holds many kinds of cargoes, and it should withstand external wave loading and internal cargo loadings. Sometimes top part, in other words, upper deck, may be partially open to manage cargoes. It's also composed of many structural elements. From this sketch, you see very complicated inside, but from this photo, the outside of the ship is very smooth, looks very simple. Usually, inside is complicated, outside very simple. This slide shows a typical part of hull structure in tanker, which carries oil. It is also composed of many structural elements such as plating, web frame, good longitudinal stiffness, etc. Most of them are connected by welding, and the section in the mid part usually very similar along the whole length. It is this structural arrangement are repeated regularly at the distance of 4 or 5 meters, so that it can be for manufacturing. For your reference, it is a rough summary of shipbuilding process, contract design, constructions, sea trial, delivery. Usually takes about 1.5 years. For construction, begins steel cutting and block fabrication and block assembly at ground as well as dock. And then commissioning and outfitting and commissioning is carried out at key wharf beside the dock. Here is a photo showing a typical shipbuilding yard where you can see a dock where 2 ships are being constructed. Here is a container ship and bulk carrier are in the same dock. Actually, docks in shipbuilding yards are very, very large and spacious. Here are three main docks and the heavy industries. In A dock, there are 4 ships are being built. in the same area. You see several Goliath cranes. It is capable of 450 tons up to 1,000 tons of weight. At this point, I'd like to mention about structural safety versus loadings. Can you see a bridge on this photo? How do you feel about that? Does it look safe or not? Whether the structure is safe or not, strong or weak, then the problem of safety depends on all the loadings. For example, in this case, weight of persons, number of people, their walking speed, wind force, etc. So loading is severe, then the bridge becomes weaker and becomes not safe. So the problem of strength and weakness is the problem of relation between structure and loading. So when we design ship, then we should think about what loadings we should include in design stage. And that's the main concept of this lecture. The design concept of hull structure is the hull should be structurally safe and functional in lifetime of 20 years under maximum wave loading. Looks like this big wave, and also repeated small wave loading. As you can see from this photo, very small wave loadings applied to the hull structure, and various cargo loadings. Finally, accidental impact loadings, such as slamming, collisions. I'll explain in more detail later. Anyway, the hull structure should be designed to ensure strength for its lifetime. Wave loadings. When we design a ship, then the ship, we assume that the ship encounters about 10 to the 8, 1 million wave loadings during her voyage. So we should consider all of those wave loadings in our design stage in calculation of structural strength. Among those waves, the maximum, in other words, worst wave bending occurs when the wavelength is equal to ship length. As you can see from this red shaded color, wavelength from here to there is about the same as the ship length. This is the case that the maximum bending moment is applied against the ship hull. And also, cyclic loading is applied by repeated by these irregular waves, which sometimes causing to fatigue cracks. This slide shows what is the maximum bending moment, sagging moment. The total moment can be split into two parts, maximum static and maximum dynamic. Static moment can be induced by cargo distribution, even in still water condition. For example, the center hold is full, then it's bent down at center, so it's applied by static sagging moment, even without any wave. And then there is also dynamic bending moment by wave. Just I mentioned before. So this static maximum and the dynamic maximum may be overlapped at certain time, then it causes the worst case of loading condition. Here are many photos showing typical ship conditions in rough seas. When designing ship structure, we need to consider all of the rough sea loading conditions so that hull should withstand the ultimate conditions in storm seas. But most of the time, the sea conditions are very calm. But during her voyage of 20 years, so it is inevitable to meet this kind of rough, very serious ultimate loadings on the ocean. In ship structure, where is the weak areas? In general, upper deck and bottom plate here, upper deck and bottom. Midships are the part of the weakest because maximum bending moment is applied in this position. So maximum stress is induced. So structural failure may happen, a crack and buckling happens. So hull structure design criteria is that crack or buckling does not occur during her voyage. Cracks. A crack is defined, refers to be a small separation of materials. Cracks sometimes occur at stress concentration areas in such as bracket, toes, and welded joints. on the structure, it occurs. The weakest point sometimes propagate across the structure. This is photo showing an example of crack grows as long as 20 meters, initiate and grew. A buckling, sometimes buckling occur at the compressive panel and stiffener. In this case, buckling refers to structural instability, such as large lateral deformation of panels under compression. In this case, the bottom plate receives compressive stresses by the hogging moment. In order to evaluate the buckling strengths, we usually structural simulation like this. Sometimes we carry out a full-scale buckling test but sometimes buckling is very important. If a panel, a small part of structure buckles, then it can grow into final collapse of the whole structure, as we see from this photo. Section of ships. Section of ship is one of the themas when we design a structure, because the rigidity of structural section depends on the shape of section. It's closely related to hull deflection. Here is an example, beam A, B, C, D. The sectional area is all the same, but rigidity differs from the shape of the section. Beam A is weak to lateral band, a strong vertical band. The beam B is very weak to vertical band. Beam D is known to be very effective for vertical, lateral, and torsional movement. So when designing our structure in the initial design, we make it the section of the ship closed section. This photo is a typical section of a tanker. The whole section is closed and inside encompassed of very small closed sections. Here are various sections of ships. Oil tanker, where we see big two closed sections. Bulk carrier, we see 3 closed sections. Container ship, there is a big opening of the deck. So we cannot make a closed section for container ship. So instead, we design small closed sections around the hole, and the thickness of the plate, this small section, should be increased to maintain a certain level of rigidity. Strength of material. In order to evaluate structural strength, we need some basic knowledge of material strength. We need to understand how stress and strain react to each other. So stress and strain are related by this equation. This material test can be obtained from the test using these small specimens. And test is done like this simulation. From this test, we need to catch the data for yield and fractures, where the material starts to yield, in what strain the material fractures. These data are usually used to evaluate stress conditions for the stress concentration areas of the structures. So we need to compare the stress level of actual structures and with this material data, and then we evaluate the structure to be safe or not. The stress is meant to be a measure of internal resistance for externally applied force. The stress is same, but sometimes stress states are very complicated. There are many components, up to 9 components, but we use one equivalent stress to evaluate the stress state. In stress-strain relation, the material constant is called Young's modulus. So the higher the Young's modulus, the more stiffer the material. So steel, for example, steels endure 3 times more forces than in aluminum. When we have an injection normal stress is very, very high due to the very small area of sectional area. Simple beam theory. Why is this important? Because ship is very long, up to 400 meters, as you saw in your slide. The whole ship can be regarded as a simple beam in the initial design stage. So this simple beam theory is used using these simple equations. Maximum stress amidships is easily calculated as like this: moment divided by some component section modulus. So stress is obtained from maximum moment calculated from wave loading, and section modulus calculated from the design section. So the meaning of design ship structure section is calculate, arrange the section of structural element to make a section modulus to be the minimum, to be the maximum, to make the stress lower. Here is an example of design of section for a bulk or tanker. In the initial stage, sometimes this simple equation very effectively used in actual calculation. But in final, in the detailed design stage, after initial design, very complicated, very fine mesh structural analysis should be performed. So initial design and later design stage, approaches are different. Usually, a stress should be lower than yield stress. For example, 90% of yield stress should be maintained. So we need to determine the size and arrangement of structural elements. Here are some examples of structural failures, cracks and buckling in reality. Ship weight is composed of hull weight and equipment and cargo. When the ship weight is equal to buoyancy, then it comes to vertical equivalence. If weight and buoyancy change, ship moves. In reality, the dynamic wave loading applies to hull, so ship keeps moving all the time during voyage. Main design loadings, hull girder loadings, impact loadings, cargo loadings, sometimes vibration and temperature may be acting as loading. Here is a good video showing ship response. Let's see it.
A simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it, from sources such as the light ship weight, the weight of cargo, ballast, fuel, etc. And of course the harsh sea, marine environment, the movement of the ship and vibrations. The hull may be compared to a simple beam. When a force acts on the beam, it bends and stretches in accordance with the magnitude of the force and the strength of the beam. Loads generate vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced in the bow due to ahead seas. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. The same simple beam principle also occurs in complex combinations inside the ship's structure, where plating, frames, stiffening, girders, panels and brackets are built up from many separate small beam elements, all working together. Due to the many and variable forces acting upon them, These elements may partly fail and develop cracks and damage in critical areas, causing a serious reduction in local and overall strength. In addition, aggressive corrosion that is found when placing steel in the marine environment ruthlessly weakens the steel and its welded connection.
Yeah, it's very useful video, isn't it? Here is summarized very global loading conditions we need to consider in the initial design stage. First of all, a vertical hull girder bending moment is most important in general. So as I mentioned before, static bending moment in still water, as well as dynamic cyclic bending moment in waves, are both considered. In this stage, we investigate cargo distribution and wave conditions. How is it combined? It is a very important question in design point. Second one is hull girder bending moment for horizontal direction. First, let's see a video showing ship motion simulation under a big side wave coming from 90 degrees. It's called horizontal side direction waves. In this condition, horizontal bending moment is induced with a large rolling motion. This horizontal bending moment sometimes coupled with a vertical bending moment, inducing the maximum stress at the corner of the deck. Sometimes it causes ship to capsize and the loss of hull stability. Next. The third one is torsional hull girder movement. In this loading condition, encounters in oblique wave conditions. In other words, wave comes from about 45 degrees, like this. In this case, the water depths, left and right side, are different. So this difference of water depth induces the rotation of the section. But the rotation direction are different from at front and rear. So this difference make the whole structure twisted. So torsional deformation is induced by like this structural simulation. For container ship, this kind of loading is the most serious. One of the impact loading is bow flare impact, where bow flare refers to the front structure above water level. So when the ship runs in head sea, sometimes very high impact loading for this bar flare, sometimes causing permanent yielding. So in order to evaluate this condition, model tests or structural simulation are performed, like this one. This red one shows very high pressure point. Next one is bottom slamming. This loading happens generally high-speed ships under vertical motion when it pitches a lot. So as you see from this photo, this induces permanent yielding and fracture, especially for bottom area. From this simulation, high-speed ship, when it pitches a lot up and down, then the bottom structure undergoes a very high pressure. Next one. Next one is collision. Sometimes it's very important when ship-to-ship collision happens. This is a photo showing an accident of collision where a big bulk carrier collided into a small tanker. Can you see a lot oil spillage around a large area around the ship? In this evaluation, we need to consider the side structure is strong enough not to be penetrated. Usually, we cannot actually test, so we carry out structure analysis using very big models. Grounding. Grounding is a case when ship ground and contact with the seabed, such as rocks. The main concern is to design a double bottom structure so that the oil inside does not flow out of the hold after grounding. This kind of accident often happens. Explosion for warship. In this case, it's limited for warships. The designer should be aware of structural response to underwater impact by explosion accidents. So we need to make proper reinforcements in order to minimize casualties and damages. We usually carry out structural simulation called FSI, fluid structure interaction, where a large amount of sea water around the ship model and the explosive are together included whole modeling. So usually it takes a lot of times and a very skillful experience needed for this evaluation. Here is a good actual test conducted by U.S. Navy showing warship structure response to underwater detonation of torpedo.
Popular belief, modern torpedoes do not actually have direct impact with the hull of a ship. Instead, they use a proximity fuse to detonate beneath the ship. This detonation vaporizes the water around the torpedo and creates a high-pressure, high-temperature steam bubble, as well as an intense shock wave beneath the keel. When the detonation occurs below the keel, the resulting pressure wave of the explosion lifts the ship, weakening its keel in the process. As the steam bubble collapses, the ship is sucked down by negative pressure and appears to momentarily sag in the middle. When the steam bubble finally reaches the surface, it explodes through the hull of the ship as the change in pressure creates another more powerful shock wave. This combined effect often breaks smaller targets in half and can severely disable larger vessels.
As I mentioned, in order to evaluate the explosion accident, we need to carry out this FSI simulation technology.
Popular belief.
Yeah, it's the last slide summarizing design loads for our structure, which are horizontal loadings, vertical, horizontal, torsional moments and shear force, impact loadings, bar flare, bottom slamming, collision, grounding, explosion. Sometimes cargo loadings, various kinds of cargo loadings are included in the initial design stage. From this presentation, you maybe have a feeling what kind of main loadings should be investigated for initial design. What loadings are important, and so on. So I hope this presentation is interesting to you. Thank you for your attention.
Thank you very much, Mr. Bach. Is there any question to Mr. Bach? No, as usual. I have one request and one
Yes.
question too. One request is, it is very interesting presentation. Can you provide the slide set to students later?
Oh, this slide, this presentation material?
Yes, please.
Yeah, yes, okay. I'll send it to you later.
All right. Thank you very much.
Yes.
Another question is about your real experience in Hyundai. My question is, did you have a chance to design a real ship which was constructed and operated, or you just do in the R&D department as a analyst for safety evaluation? What was your real experience in heavy
My
industry?
main work was in R&D department, and the main job was evaluate the structural strengths for the structures designed in the design department. But for several years, I actually worked in design department also. So I actually designed a few ships.
Oh, is it? So what kind of ship or structure did you design really in the design
Those,
office?
yeah, I remember I was involved in designing tanker, bulk carrier, container ship, car carrier, yeah, etc. I was not involved in LNG carrier. LNG carrier also was.
Oh, so
little
many
bit.
ships. You already designed so many ships. structural design.
Yeah, I was in Hyundai 35 years.
But as a real design office, the design department, you said you worked in only 3 or 4 years in the design department?
Yeah, 2 years in design department, and then R&D.
Okay. So during those two years, you designed many ships.
Oh,
That is
initial design. Initial design is not detailed design, so
okay.
I could involved in initial design.
All right. Thank you very much. Any
Thank
other
you.
question to him? No? Then we can close this nice lecture day. And you see on Thursday at the classroom for the final lecture and discussion. All right. Thank you very much.
Thank you.
We close the session.
감사합니다.